Okay, so let's start. So first I want to apologize for missing Monday. So nothing I could control really. But this is actually the only the second time this has happened to me in 22 years, I think, of teaching. So not too bad. So again, I'm sorry. So let's see where are we. So we talked about online algorithms, multiple versions. Most of them turn out to be really stochastic gradient descent algorithms. And notice that when we say stochastic gradient descent algorithms, it's a family of algorithms that takes as input a loss function. Once you have the loss function, you define the algorithm. And some of these, specifically perceptron, turn out to be also mistake-driven in the sense that you don't update unless you make a mistake. So this was one sort of key component. The reason I say most turn out to be stochastic gradient descent algorithm is that we also talked in passing very quickly about Wino, but you got a more detailed definition of it in the homework. And this is, strictly speaking, not a gradient descent algorithm. It's what is called exponentiated gradient descent because it's multiplicative rather than additive. We then suggested improvements to the basic gradient descent algorithm, really in three ways. One of them is the kind of generic way of doing it by adding regularization. So we think about the loss function itself, the Q, which minimizes the error on the training data, plus another component that forces simple hypotheses. We still don't know why this is important and why this actually forces simple hypotheses. You have to take it for granted, but we'll see it in the next week. A second addition that we had was the average trick, sort of not learning just one linear function, but rather keeping multiple linear functions and using the final prediction, doing the final prediction with an average version of them. And this is actually a more stable hypothesis that one can one can say a lot of good things about it. For people that are really interested in how this works and why this is so good, we added a paper, a pointer to a paper across from this lecture. So look at this paper. It explains things very well. It also has, by the way, the proof of perceptron, which I put on one slide here, but I didn't go into the details of it. And the third trick that we added is the improved update rule by changing the learning rate, which we call undergrad. So with all these, now you have a bank of good algorithms to work with. You can always think about this regularization using this picture that I put there and the top right. So we are after a linear separator, which is the solid blue separator. But really what we are after is kind of a thicker version of it. And in some sense, the question is how to get to this thicker version. And what we'll see is that the regularizer, this part here, these two, really do that explicitly. I mean, we'll see that and we'll understand this better as we go. Okay, so in the course of doing that, we also talked about the function space and the instance space properties. by function space, and basically we talked about sparsity. Sparsity in the instance space means you look at examples, let's say they are binary examples, zeros and ones, and in many interesting cases, most of the features are zeros. So it's sparse. We also talked about sparsity in the function space. So you have a W that you're learning that has high dimensionality. In real problems, it could be hundreds of thousands or more. But really, very few of them are important. You don't know which are important, but very few are important. And that means sparsity in the function space. And we talked a little bit about the dependence of learning on that, and you will see more of it in the problem set. And that's a good time to take questions. Before I even take questions, I want to say, I know that quite a few of you had questions about implementations of the algorithms or what you observe. Please go to the recitation. There is one today, there is one tomorrow, a lot of office hours. Please go and ask questions. Questions here, now. Yeah?
When we're taking the average to regularize, we just average it, we take like the number of correct predictions over the number of total mistakes, or the number of like iterations times the number of examples per se?
I'm not exactly sure what you're asking. Let's go to this. Here. So C is going to count how many examples. So CI is going to count how many examples the hypothesis VI survived. So you got to VI, and now you take an example. You did not make a mistake on it. CI is 1. You take another example. You didn't make a mistake on it. CI is 2, and so on, until you make a mistake. Once you made a mistake, you put VI to the side, because now it's going to be VI plus 1. You updated it, and you also have CI on the side. So now ask your question again.
So yeah, so if we say that we're taking an average, are we actually, so in that bottom line over there.
Yeah, this one.
Yeah, so are we dividing CI by the total number of mistakes we make? Are we dividing it by n1?
Oh, it doesn't matter really. Okay. You can do average, but if you divide it by a fixed number, it's going to be the same sign. Okay. So yeah, you can if you don't want to count large numbers, you can average. But it's really the same function. Yeah.
So I understand how that applies to hypotheses that only change when they make a mistake, but how does that apply to hypotheses that you update each time you go make a mistake?
When do you do this? None of the algorithms we gave you is like that.
So I guess, can it be applied to non-distributed?
Not this way. You can average, but you'll have to do other things in order to average. But in the homework, we gave you Winnow, perceptron, and undergrad perceptron. All of them are mistake-driven, so simple. In general, this notion of weighted hypothesis exists. But the average perceptron is really for, the way it's written here, it's for mistake-driven algorithms. So it's true that the notion of averaging is a general notion that is useful, but this specific version of weighted hypothesis, we've written it for the case of mistake-driven. Questions? Okay, so one additional comment. So you have two parts for the problem set. One is dealing with the synthetic data that we've generated for you. where we kind of had control on what data you will see, and we generated data so that you will see differences. So hopefully you will see differences. And you also have real data. Two comments about the real data. One is part of the real data is actually not open to the public. It's under license, and you get it because you're students at UPenn. Please don't distribute this data. It's given to you only as students at UPenn. Two, it's a very high dimensional data. You will see it when you extract the features. It's also very sparse, but it's very high dimension. So you'll have to think a little bit, or you may need to think a little bit, because some of your algorithms that worked in seconds on the synthetic data will not work in seconds on the real data if you don't do the right thing. So just think about it. And again, don't wait until the last day, because it may take you some time to think about it, and you may want to come and ask questions. But I think you'll see interesting things when you run it on the real data. Questions? Okay, so that's what we did so far. What I want to do today is move to discuss the notion of kernels. Basically, how to deal with nonlinear target functions when the data is nonlinearly separable. And if we are lucky, start talking about learning theory. Before that, I want to remind you two important administrative things. One is midterm. Midterm is coming up. We changed the date of the midterm. It's going to be October 31st in class, Wednesday, I think 2 weeks from today, or something like that. And I also want to remind you that project proposals are coming up. So several of you sent me email and came to talk to me. Most of you haven't. I'm assuming that you are on it. So, okay. Questions on that? No, okay. So we talked about generalization of the algorithms and promised that the algorithms that we talked about will generalize well. There's one other aspect that we often want to think about, which is efficiency. So all these are linear algorithms, so they're really simple. Every step of update is very simple, but it's dominated by the size of the feature space. If you have 200 features, 1,000 features, a dot product is going to be cheap. If you have 1,000,000 features, a dot product is going to be expensive. And you will see that when you work with the real data in your homework. So one question is, can we save on this dot product operation? And this is mostly important when we blow up the feature space. So in real life, this line here indicates that in real life, often the observations that we have are x1 up to xk. These are basic measurements that we take on the input. You can think about it, and then we take some functions of this, right? So if you remember when we talked about context-sensitive spelling examples, what we see are words. And what we decided to do is we decided to look also at conjunctions of words. Not only single words, but also this is the word before and this is the word to before. Or this is word one after my target and conjoined with the word after. So what will happen is that the number of features, n here, is going to be much larger than k here. Which means the dot product is going to be done over a lot more features. Can we do something in order to do this more efficiently? So really the image that you want to have in mind is this. This is the data. These are the original observations that you see. This is, K here is 1, right? Because you have one measurement on each example. K from this slide is 1. And you can see that you cannot learn a linear function, right? Separating blue from red here requires a more expressive function. But if you change to n equal 2, now you have 2 dimensions, okay? So again, from the previous slide, K was 1, but I blew up the feature space, and n is 2. And now I can separate it linearly. So that's what we are after. Here is another example that could be interesting. So what we want here is to separate green from blue. And the function is 1 if and only if x1 squared plus x2 squared is less than 1, right? So you get this circle or oval shape. Now, this function is nonlinear in x1 and x2. What can we do? We can change the feature space. And now, instead of the feature x, which is x1, x2, I'm going to move to another feature space, the squares. In the squares feature space, it looks like this, right? So all I didn't add any information. All I did is I changed the representation of the data, and now the data is linearly separate. That's what we want to do, and this is where the idea of kernels come in. Okay, so we're going to, in order to deal with it, we're going to introduce something that we call dual representation and use it to discuss kernels and what is called the kernel trick. So we already started to talk about it at the end of last time, where I kind of challenged you to think about what is really RW. And we agreed, I think, that if we take perceptron, so let me just add one side comment. In many places, you will see, and I'll mention it later on, but I want to motivate what I'm doing here. You will see kernels in the context of support vector machines that we'll get to in about 2 weeks. Deliberately, I teach it in the context of perceptrons for 2 reasons. One, it's much simpler in the context of perceptron. 2, I want you to realize that it's not part of SVM. It's really part of a lot of linear separate or linear functions, the property of being able to use kernels. It was popularized in the context of SVM, but this is just kind of the social side of science more than the technical side. It's much simpler and clearer if we do it in the context of this very simple algorithm. So what are we doing? This is all of perceptron. You know this by heart now. Hopefully you played with it already in the context of the problem set. And the question that I want to understand is what really happens to the W and what happens as a function of it to the prediction that we're making. So here is the scenario that we have. I started with W. I have 4 examples, plus, plus, minus, minus. And I told you that it so happened that as we went through this data, we made mistakes on x1, x2, and x4. And the question is, what is the resulting weight vector after you've observed these 4 examples and updated it? And the answer is? You all should be able to do this now. So this shouldn't be difficult. So we start with W. We see x1. We make a prediction. Yes?
x1 plus x2 minus x4.
x1 plus x2 minus x4 plus W. We started with W. Yeah. So why is that?
Because at the beginning, the label was passed, but we made a mistake on it, so we want to make sure that we get the pass.
So we add x1. And then same thing with x2. No mistakes on x3, so it does not contribute to the weight vector. Yes, mistake on x4, so we subtract it. Everyone is clear on that? And here I took R to be 1 just to simplify things. So the learning rate is 1. Okay, so we know how W looks like. And basically, in general, hopefully I convince you that I can write W as this linear sum over all the examples that I observed. R, which is the learning rate. You can think about it as 1 and eliminate it from here. Alpha I times yi times xi, where the alpha I is the number of mistakes we made on xi. So if I had made no mistakes on xi, basically xi, the coefficient of xi in this sum is going to be 0. It's not going to contribute to W at all. If I made a mistake on it, it's going to contribute 1. If I made 7 mistakes on it, it's going to contribute 7. And yi is going to be plus or minus 1 to tell me whether I added xi, or subtracted it. Now, so that's W. So the interesting thing that you now get is that the weight vector is really a linear sum over the xi's. Now, we don't really care about W. We care about the prediction that we were making given W. So we care about W dot product with the new x that we get. So let's assume we get this new x. I want to compute f of x. X is a new data point. So I need to compute W transpose dot product x. I'm substituting the W that I have here on the side with x. So that's the prediction, right? That's how we predict. And I'm going to propagate x inside, which means I have a linear sum, 1 to m. These are all scalars, numbers. And here I have a dot product between xi and x. So what does that mean? If I want to know the value of the function on x, what I need is I need to remember all the previous examples that I've seen, xi. And when you give me a new x, I'm going to compute the dot product of this x with all the previous xi's and do this linear sum. Okay? Now, in fact, I don't need to remember all the xi's. What xi's do I need to remember? Only those I made a mistake on. Because those that I did not make mistakes on, I can throw away. They don't matter at all in my prediction on the new x. Okay? And now you can see that there's no notion of W at all. Everything is in terms of examples. And this is what we call the dual representation. Okay? So the dual representation of the function is a representation of it in terms of the data rather than a weight vector. Why is this important? It's important because this is the basis of kernel-based methods. So kernel-based method, as we'll see in a few minutes, is a method to run perceptron or other linear algorithms on a very large feature set without incurring the cost of a lot of features. The idea is that eventually we will show that when we think about it in the dual space, we can compute this dot product. Right? Think about it. Here I'm doing dot products. Instead of doing it in a blown up space, I'll be able to do it in the original smaller dimensionality space. And a comment that I'll say later on, because in the literature sometimes it's confusing, using kernels gives you nothing in terms of generalization. It doesn't change the algorithm at all. It's the same classifier you would have used had you just blew up the feature space without kernels. It's just efficiency. It's a cleverer way to compute. Okay, I already said that. So let's start. So I'm going to basically do this via a running example. And the running example is going to be the following. So we're going to think about working in the Boolean space. Our examples are going to be 0, 1 to the n. So this is my function, right? So it's the sign of the dot product WTX, or explicitly written here. And I'm going to first blow up the feature space. So instead of working with x1 up to xn, I'm going to work of conjunctions over x1 to xn. In fact, I'm going to work over all the conjunctions. I'm going to call it sometimes monomials. So I is going to be the set of all monomials over the x1, xn. So this will be x1 and x2, x1 and x2 and x3, x1 and not x2 and x3, x1 and x2 and not x3, and x4, and so on. So here are examples. What does it mean? So if my example, my original example is 1, 1, 0, 1, 0, the left one that you see over there, and I have now a monomial, so now my feature space is the set of monomials. One of them is x1 and x2 and x4. So I don't put the and here. I just leave it as a product. So what is the value of this monomial on this example? It's 1. Hopefully you agree with me, because both x1 and x2 and x4 are on. So it's 1. The value of x3 and x4, the monomial on this example is 0, and so on. So essentially what I'm doing is I'm taking an example. It's a 5-dimensional example, and I'm rewriting it in a new dimensional, in a new space, where each feature in this space, each dimension in the new space is this monomial. How many monomials do I have? If I started with n, think about it. I'm going to ask it again. But look at what I've done here. So now, this is the function I'm running. So instead of the function over there, linear sum wi xi of x, you can always think about xi as xi of x. It basically says, look at the xi value of the example x, right? So when I say the ith feature of the example, it's really a function of the example, right? It's basically go to the ith component and read what's there. Simple function. Now I'm moving from this to this. So now it's sum wi ti of x. Now the components, the features are the ti's. Okay? And I'm going to run perceptron on this, only that now this space that I show you at the top there is huge. A lot more ti's than xi's. So it's the same idea, the same dot product, only that it's going to cost me more time to compute. So we will suffer exponential growth, by the way, also in convergence, because the dimensionality is much higher. So, okay, and we'll have to keep many ways. This is really the same example that we talked about some time ago. I'm starting with this feature space on the left, which is the xi feature space. The function in this feature space is complex. I'm moving to a new feature space where the dimensions, each dimension is now a conjunction, but the functional form is simpler. Clear? Questions? Yeah. So TIs are conjunctions, like this. So if I have 5 dimensions, TIs are conjunctions with up to 5 sides. So for example, a conjunction like this, x1 and x2 and x4. Now, let's think about how many conjunctions like this are there. I have 5 dimensions. How many conjunctions can I write on 5 dimensions? Why 5 to the 5?
So you can either just, I guess, but you either just have each example just on its own, or you can have each example with another example.
No, but the conjunction is among the features. This is an example. x1 is 1, x2 is 1, x3 is 0, x4 is 1, x5 is 1. And then I'm writing a conjunctions over this. So the conjunction could be of size 0. empty set, or it could be of size 1. How many options of size 1 do I have? 1 second. How many options for conjunctions of size 1 do I have? It could be x1. It could be not x1. It could be x2. It could be not x2. 10 options. Now conjunction of size 2. I can have x1 and x2. x1 and not x2. Not x1 and x2. Not x1 and not x2. And then I can have the same thing with x1 and x3. And so on. Altogether, how many will I have? So think about it, yes.
2 to the 6.
2 to the 6. Why 2?
So you'd have 2 to the 5 for all conjunctions without negation, and then 2 to the 5 more for with negation?
Almost. 2 to the 5, it's true without negations, and the rationale is that I have 5 spots. And in each spot, I can decide whether I put x1 or I put x1 negated. Or sorry, let's do your case, which is just monotone conjunction. So in each spot, I can decide whether I put xi or nothing. I don't put this variable. Right? So I'll have 2 to the 5. I have 5 locations. Now, if I allow you negations, in each spot, what can I put?
So you have 3 options in each spot. You can either exclude it, you can put the controversion or the negation. So it's 3 to the 5.
Right, so think about exactly that. I have 5 places. The place for the x1, the x2, x3, x4, x5. In the first place, I can decide, do I put x1 here? Yes. Either yes or no, or I can put it negated. Same thing for x2, same thing for x3, x4, x5. So I have 3 options to the power of 5. For example, what did I decide in this case? In this case, I decided not to put anything in the first place, not to put anything in the second place, to put the positive one in the third place, the positive one in the fourth place, nothing in the fifth place. Okay? So altogether, in this case, because I have 5, I have 3 to the 5. Yes?
This is only for Boolean features?
This counting is only for Boolean features, yeah. If I had features that have 7 values, I will have a lot more options. But I'm just giving an example of Boolean functions, which is a very common example. In most applications, or in many applications, your input is going to be Boolean features. So we're going to play this game now, because conjunction over Boolean features is what you're going to do there. If you have multi-value features or continuous features, we're going to get to these examples a little bit down today. How to do similar things over this. But I want to push this example. So in general, so basically, we did nothing, right? We basically blew up the feature space. And in fact, I want to make sure that you understand what we did. So go back to this example, right? So this example will illustrate what is the new feature space. So now you can take a feature space, instead of 5, it will be 3 to the 5, okay? So it's a large feature space, and you will have some order of the TIs, and still it's going to be a binary feature space, right? In each, let's assume that this guy is in the 17th place out of this 3 to the 5 dimensions. So in the 17th place, you'll have 1. In the space x1 and x2, and x3 and x4 and x5, which is another monomial, you will have 0, and so on, right? So you'll have 3 to the 5 dimensions. In each place, you will have to take the example, the original example, the 5-dimensional example, 1, 1, 0, 1, 0, and you'll have to compute whether now it's a 0 there or a 1 there. Okay? Very similar conceptually to what you'd have done with the decision trees, where you move from one space of 390 to another space, only 200s, where, again, in each location in the 200 space, you decided whether to put 0 or 1 by evaluating a decision tree. Now, you're doing the same thing, but you are evaluating a conjunction. Questions? Okay. So now we have a perceptron. Same update, only that we have it over the TI space. And we can, again, think about what is the W that we're going to compute. As we said, how do we compute the W? For every mistake on example Z, we are either adding Z or subtracting Z from the W. And therefore, the value of W is completely determined by the example. So let's just write this down more explicitly. So let's assume that P is the set of examples on which we promoted, that is, positive example on which we made mistakes. D is the set of examples on which we demoted the weight vector. M is the union of P and D. These are all the examples I care about. I do not care about examples on which I did not make mistakes, right? So now what's going to be f of x? F of x is the sign of the linear sum wi ti of x. And now let's write it down. So that means that it's the sum of 1 over all examples in P minus the sum of 1 over all examples in D. Now, remember that the examples are Boolean here. So really, only TIZ, for which it's 1, are really added to the W. So think about your W here. We're sitting on W, component 7 of W, W7. If the example, the corresponding example, has 0 in coordinate 7, W7 is not going to change, right? You're adding X to W or Z to W. If the component is 0, nothing is going to change. If the component is 1, it's going to change. So I can write it. So again, I'm reading what I've written there. It's the sum of all the examples in P such that Ti of Z is 1 minus the same thing where the example is taken from D, sorry. And all this is multiplied by T of X, right? So essentially what I've written here, this is W. Okay? This is just writing in a more complex way the exercise that we did earlier, W plus X1 plus X2 minus X4. It's just written here. Now I'm writing it in a slightly different way, where I'm going to call all this S of Z. So let's do this in a more explicit way. So I'm going to denote by S of Z either 1 or minus 1. 1 if Z is taken from P, that is, it was a positive example on which I made a mistake. Minus 1 if it was a negative example on which I made a mistake. So basically, what I have here is this linear sum. So summing over all the examples now, S is either plus or minus 1, whether it came as a positive example or a negative example, Ti of Z, Ti of X, where Z ranges over all these examples. Okay? So all I did here is just algebra. You want to make sure that you agree with this algebra, but think about what has happened. So I've written again f of x. X is this new example that I now got. Z's ranges are all the examples I've seen before. And I'm writing f of x as a function of my performance on all the previous examples. Okay? So again, it's just sum over all components, over all features, sum over all examples, S of z, Ti of z, Ti of x. I can take S of z outside of the I sum, because it's just a fixed number, plus or minus 1. Depends on the examples, not on the features. And I can also invent a new notation, which is this. So that's the function that we got at the top there. Sum over all example, S of z, and this linear sum. Now notice, so I'm going to call this k of x and z, just a notation. What is this here? If you had to describe it in words, what would you say k of x, z is? It's a linear sum, Ti of z, Ti of x, over I. What is this? I hear some suggestions here and there. What is the linear sum, Ti of z, Ti of x? Yeah? It's a dot product between the Ti representation of z, a vector, and the Ti representation of x, right? Everyone agrees? So you have components, you have dimensions, Ti, T1 of z, T2 of z, T3 of z, T100,000 of z, and then the same thing for x. These are two vectors, and what's written here is the dot product between them. Okay? So that's what we got. So basically, we got that f of x, the prediction of my function on x is, forget the threshold, this is basically just says if this is greater than theta or not. But basically, it means sum over all the examples on which I made mistakes, S of z, k of xz. Again, remember, what is z? Z ranges over all the examples I've seen before, and x is my current example, the one I care about. So essentially what I've done is I rewrote how we compute perceptron. Yes?
Just to fully clarify, even though you kind of mentioned it a few times, when we're looking at z, like our current x, it's only like the mistakes we've made previously and not all the mistakes.
Yeah, so now I'm sitting on the 53rd example, and I want to know how to predict. I'm looking at the 52 example I've seen before. This is what z ranges on, okay? And I'm computing, so essentially what do I have? I have Ti of x, or T of x, all the dimensions of x. Now, if you did not touch x, you didn't blow up the dimensions of x, this is just x. But I want to write it in more general because we will care about it when I actually blow up the dimension. So it's Ti of x. And for each one of the z examples I've seen before, I have the T of z. And I'm just computing all the dot products. So essentially, if I made 50 mistakes before, I'm going to compute 50 dot products, sum them up. Okay? But I never do updates anymore, right? So all you do is you keep the bank of all the examples. Whenever I give you a new example, you go to this bank of examples, compute the dot products, sum them up, and you have a prediction. So it's just an alternative way to compute perceptron. Okay, so what does it give us? So far, it gives us nothing. All we did is algebra. We figured out that in order to make a prediction on x, you have to compute this x. So in some sense, we agree that this is a dot product. You can also think about the dot product as a distance between x and z in their t-space representation. If you think about it, dot product is very related to a distance, or is a distance between vectors. So far we've done nothing. Why do we do this, though? The reason is that k of xz can be measured in the original space before the blow-up without actually writing down the t representations of x and z. So that's the key trick. And in order to introduce the trick, I had to do this algebra. I had to rewrite the perceptron this way. So now, what are we going to do? So let's first give an example of the value of this trick. So we have a space of 3 to the n monomials. We agreed on that, right? It was 3 to the 5 in the previous example. In general, if the dimensionality of x is n, 3 to the n monomials. So I'm arguing that computing k of x comma z, which is this dot product, sum over all dimensions, ti of z, ti of x, can be computed as this 2 to the power of same xz, where same xz is the number of features that have the same value for both x and z. So before we prove this, what does it mean? So in principle, if x has dimension 5, you said that t of x, t of z, is going to have dimension 3 to the 5. How much is 3 to the 5? A lot, okay? A large number. So originally, if you just look at this left side of this dot product, you should write, it will cost you 500 steps to do it, right? Because you'll have to touch all the 3 to the 5 dimensions. What I'm saying here is, so this is the 3 to the 5 dimensions. What I'm saying here, you don't bother. Just look at the 5-dimensional x and z, count how many of the features have the same value, and that's it, you're done. Take 2 to this number. So that's the value of the trick. Now, this specific claim is specific for this representation, this monomial blowing up. Every time, every kernel will have its own formula here, but that's the idea. So let's just play with it a little bit and convince ourselves. So, okay, that's just putting it, substituting it in the formula above. Let's take this example. And I'm going to give 2 examples. You will have to take a piece of paper at home and do this example yourself to convince yourself that I'm right here. Because some things are going to be potentially not completely clear. But let's play with it. So let's assume now that n is 3. I'm taking 2 examples. X, the one I care about, the example I care about now, is 0, 0, 1. Z, one of the examples I've seen in the past and made a mistake on, is 0, 1, 1. So the monomials I'm considering are 0, 1, 2, 3, of sizes 0, 1, 2, 3. 0 means no monomials, say 1 all the time. Monomial of size 1 is x1, not x1, x2, not x2, x3, not x3. Monomial of size 3 is x1 and x2 and x3, not x1, not x2, not x3, x1, not x2, x3, and so on. Altogether, because n is 3, we're going to have 3 to the 3. Okay? So only 27 dimensions. That's easy to do. So what you could do is you could take x and write it in a 27-dimensional space. You can take z and write it in a 27-dimensional space and compute the dot product. Okay? That's what this is, right? Take a 27-dimensional space, compute the dot product. You'll get something. I'm claiming don't do it. Just look at the 3-dimension. Look at how many of the bits are similar. So how many are the same here? 2. So I'm claiming that 2 to the 2, 4 is going to be the value of the dot product. What does that mean? It means that when you take the 27-dimensional spaces, 2 vectors of 27-dimensional spaces, my claim is that the dot product is going to be 4, which means that what is dot product? You look at it component-wise, only 4 of these are going to have matching ones, right? This means that the value is 4, right? No other configuration will do it. Agreed? Yes? Yeah. Oh, I just give an example of it's going to be eventually you do it for all the z's, right? So there's going to be a sum here over all z's. But now I'm talking about one element in this sum. So I took a specific z, I took this z, 0, 1, 1, and I'm showing you how to compute it. Later on, you'll do the same thing for all z's, okay? So again, what are we talking about here? We started with dimensionality 3. We blew it up to dimensionality 27. And you have 2 options. You can compute the dot product in the 27-dimensional space. It's going to cost you some time. Instead, I'm telling you, don't do it. Don't even blow up the feature space. Just look at x and z. Look at how many of the bits are the same there, and you tell me that it's 2. The dot product is going to come up to be 2 to the power of 2. First of all, do this exercise. I'm going to try to give an argument here. So, or maybe someone wants to risk giving an argument, why it's going to be 2 to the same. So essentially, what you want to think about is you're writing all these conjunctions there, right? So what conjunctions are going to survive the dot product? This is how you want to think about it. So for example, you have to choose a conjunction that will survive, that will give you 1 when you do the dot product. What does it have to be, this conjunction? Let's assume you take as a conjunction x1 and x2 and x3. What's going to happen? It's going to be 0 on x. It's going to be 0 on z. Right? What conjunctions are going to even be 1 on x? Give me an example of a conjunction that will be 1 on x. And x3 and? x3 is a good example. x3 is going to be 1 on x. Is it going to be 1 on z also? Yes. So here is an example of a conjunction that survives on x and on z. So if you go to the 27-dimensional space and you find the place where the conjunction x3 is, let's say it's the 17th place, this is going to contribute 1 to the dot product. Agreed? What else will contribute 1 to the dot product?
Not x1 and x3.
Not x1 and x3. not x1 and x3 is going to be on for x1, for x, everyone agrees? And it's going to be on for x3. And therefore, it's one of the coordinates that will contribute to the dot product. Now, let's take this not x1 and x3. Can I lengthen it? That is, can I add an x2 there in some way or form? Two options, either x2 or not x2. Can I add it? So I have not x1 and x3 that you gave me, and this is a conjunction of size 2, right? Can I make a conjunction of size 3 that will survive on x and z? Why not? Because they disagree on x2, right? So if I try x2, one of them will fail me. If I try not x2, the other one will fail me. So not x1 and x2 is the longest monomial that I can use. Everyone agrees? Now, what about subset of this x1, not x1 and x3? If not x1 and x3 survives, it means that all the components of it also survive because it's a conjunction. Conjunction means it's on if each one of the component is on. So not x1 and x3 survives means not x1 survives and x3 survives. In fact, all the subsets of the surviving monomial are going to survive. Agreed? How many subsets are of something of size k? 2 to the k. Okay? That's a subroutine. If you haven't thought about it before, take it as a subroutine. And in this case, just count it. You start with not x1 and x3. Not x1 is going to survive. x3 is going to survive. And the empty monomial, none of them is going to survive. So 4. So that's what we are doing here. So this is my example here at the top left. It basically shows what we just said, which is I'm starting with not x1 and x3. Red is not. You see the red? Red is not. So not x1 and x3 of x is 1 and of z is 1. And therefore, what I show here is that they are going to survive. And because they survive, every subcomponent of them is going to survive. So this is a proof. I just did the proof for this case of n equal 3. But hopefully, so why did x1 and x3 survive? Because these are the components where x and z agreed on, right? When they agreed, I chose to put this feature into my surviving, longest survivor conjunction. And therefore, same of xz is important. It determines how long the surviving conjunction is, and then I take 2 to this power. Okay, so hopefully I convinced you. Here is another example that you will play with at home. Take x to be 4-dimensional, x1, x2, x3, x4. Now the blow-up space is going to be 3 to the 4, which is 81. Take these two examples, x, my target example, and z, one of the previous examples that I've seen and made a mistake on, and write down I of x and I of z. So the 81-dimensional representation of x and the 81-dimensional representation of z. Okay, it's going to take you some space, so write it in 2 rows. As you're writing it down, decide on some order. It doesn't matter which order, but you have to decide on an order and be consistent. As you're going to start writing it, you'll convince yourself that everything we're saying here is right. So you want to compute the dot product in the 81-dimensional space, I of x, I of z, and you want to show that this product, this dot product here, is really 8, which is 2 to the same between x and z. Same in x and z is 1 here, 2, 3. Okay? There are 3 bits that are the same, and therefore it's going to be 2 to the 3, which is 8. So if you write this 81-dimensional vector, or on the way to writing all of it, you will already convince yourself that some of the dimensions, there's just no point on writing them because you know they'll not survive. And you will realize what dimensions you really care about. Okay, done with this. What have we done? And of course, this is a specific kernel. You can think about inventing other kernels. For example, kernels of only conjunctions of size 3, not all conjunctions. And then you'll have to invent or to argue why is this a kernel, unless you go to the next few slides, and I'll give you a general principle of what is a kernel. But what have we done so far? We basically said, let's move to the dual space and run, rather than simple perceptron or primal perceptron, run dual perceptron. How do we do it? We run perceptron in an online mode, keep track of the set M. Those we made mistakes on. If we keep this set, we know S of Z, which is the sign of the example, positive or negative. And rather than remembering W and updating it, we just remember M, and that's it. And this is how we make the prediction every time, by summing over M examples, this linear sum. Okay, so let's take another kernel. So this was all devoted to a single kernel, and hopefully gave you the idea of what does it mean. But of course, there are many other kernels. And everything we said so far is that prediction with respect to the separating hyperplanes, the function that we have, can be computed as a function of dot products of feature-based representation of the examples. Basically, that's so we want to define a dot product in a very high dimensional space, like this. So take two examples, n-dimensional examples, and I want to be able to map them to a higher dimensional space. Here I'm going to give you the quadratic blow-up space. So I'm moving from n to this space, 1, n, all the x1 up to xn, all the squares of x1 to xn, and all the mixed squares, x1 and x2, x1 and x3, up to xn minus 1 and xn. So here I have about n square features, right? And now I want to do the dot product. So what did I do? Someone gave me examples in n-dimensional space, but told me, you cannot learn a linear function of this, because it's not going to be linearly separable. But if you move to the quadratic space, the original example that I gave, move from the linear line to the quadratic case. If you move to the quadratic space, everything is going to be linearly separable. Do it. So that's what I'm doing. I'm taking x, and I'm transforming it to phi of x, which is n square dimensions. Now I have two options. I can compute A, the quantity A, which is the dot product between phi of x and phi of y. Every time I'll have to do this. Or I can compute B. And B is going to be a quantity that I compute directly in the original space. I'm not going to blow it up. And I'm telling you what is B. B is essentially the dot product of the original x and the original y, plus 1 all square. Much easier to compute, okay? This is just an n-dimensional operation. A is an n square dimensional operation. I'm claiming that A is equal to B. I'm cheating a little bit. Really, I should have put square root 2 coefficients on the quadratic terms there, but forget about it because it doesn't really matter. When you do the algebra, you will see that you need square root. So what is the trick? Because A is equal B, it means you want to work in the quadratic dimensional space? Good. But you can do it just by working correctly in the n-dimensional space. So that's the kernel trick. We'll see it a few more times. What did we say? We want to work with degree 2 polynomials, phi of x. If we do that, the dot product will be in the space of dimensionality n squared. n plus 1 over 2, exactly. The kernel trick allows you to save and compute dot product in an n-dimensional space. That's it. Okay, so now that we have a trick and two examples, can I choose any k of x xz that I want? Any function of these examples will do as a kernel. Again, what is a kernel? A kernel is something that satisfies this trick, that you give it high-dimensional vectors, and instead of computing the dot product in the high dimension, you actually have a way to save it and compute it in the original space. Any k works. Turns out that not every k works. Not every k can be plugged into this f of x. A function k of xz is a valid kernel if it corresponds to a dot product. Sometimes you'll see it as an inner product in some feature space. So if it corresponds to a dot product, then it's a legitimate x. Let's give another example. Here is another kernel. You want to compute, to use k of xz as dot product x and z square. That's what you care about. You want to use this as k. Is it a legitimate kernel? What we're going to do is we're going to try to directly show that it's okay. Let's take the example of 2-dimension. So x and z are 2-dimensional vectors. So I'm writing your proposed k of x and z here. So it's x1, z1 plus x2, z2 squared, right? This is another way of writing this. Everyone agrees? Now let's open the parentheses here. That's what I get. And now I'm imagining a way to factor it into another dot product. And here is what I get. This sum can be written as x1 squared. It's a dot product of 3-dimensional vectors of the following four. x1 squared, square root 2 x1, x2, x2 squared, and the same thing for the z. Now, if you take this dot product, I argue that you will get this. Okay? If you believe it, what you've shown is that you can take this k of xz and write it. Now, x and z are 2-dimensional vectors, and you can take this k of xz and write it as a dot product of 3-dimensional vectors. I call these 3-dimensional vectors phi of x and phi of z. So what did I do? I showed that this is a kernel because I wrote it as a dot product of vectors. Okay? Whenever you invent a function over two vectors, x and z, either it's directly a dot product. You can just say, okay, k of xz is k x dot product z. That's cheap. But you want a more complex function. If this more complex function is itself a dot product, it's a good kernel. You can run perceptron on it. So that's what we've proven. Now, in general, and basically this is this example. The example that I showed before, when I take x1, z1 plus x2, z2 all square, is this example that moved from this original space to a linearly separable space. Okay, so in general, it's not necessarily to show the feature function phi. It's enough to show some property. So you can take your desired k of xz, write it as a matrix, right? So take all the examples that you have, and in the ij place, write k of xi zj. So now you got a matrix, okay, over all the data. if this matrix is something that is called positive semi-definite, it's a kernel. Now, in the next few slides that I'm not going to go over, there's some more discussion of what does it mean. We don't need it. Instead, what I want to do, I'm going to give you some examples. So what are examples of kernels? Clearly, the linear kernels, x dot product z is a kernel. We already showed that polynomial kernel of degree 2 is a kernel. And I'm arguing that the polynomial kernel of degree d, so take the dot product of x and z to the power of d, it's a kernel. You can also take polynomial kernels of up to d degrees, which means add a constant here. Take the dot product xz plus c all to the power of d. So we actually saw both these examples for the case d equal 2 and c was 1 in previous slides. So just go back and make sure that you agree that we actually showed explicitly that these are kernels. And there could be many, many other kernels. You can construct kernels. And there are multiple rules for how to construct kernels. I'm not going to go in details over all of these. But basically, if you take a kernel and multiply it by a constant, it's a kernel. If you take a kernel and multiply it on both sides by a function of the first argument and the same function of the second argument, it's still a kernel, and so on. How do you know? And there are a few other things. So in all these cases, you can easily prove that this is the case. For example, let's take this example. Adding two kernels is a kernel. How do you prove this? How do you argue that this is the case? You know that K1 is a kernel because I told you, which means there is some phi of that K1 of x, x prime, is a dot product, phi of x, dot product with phi of x prime. And the same thing happens for K2. There is a phi 2 such that K2 of x, x prime is phi 2 of x, dot product with phi 2 of x prime. From this fact, you have to show that there exists phi 3 that is the dot product here. So again, it's a little bit of understanding the definition plus some algebra will allow you to convince yourself that this is also a kernel. And this way you can construct a lot of kernels. As I said, in all cases, it's easy to prove this directly by construction. I want to make sure that you understand what we are doing. So, okay, I think I'm going to stop here. We have a little bit more to talk about kernels, and then we're going to move to other things. As I said earlier, everything I did today, you have to take a pen and pencil and paper, and go over it and convince yourself that the algebra is right.
Is the whole idea of kernel to just have it faster and more computationally efficient?
That's the only idea.
So is it always gonna, so if you can make it into a dot product, in that sense that we did it, is it always gonna make it computationally more efficient? In the example that you gave us, x1, so in the last example, that you made into a dot product using square root of 2,
Yeah.
was that more computationally efficient?
Yeah, because I changed from dimension 2 to dimension 3. So instead of working in dimension 3, it's sufficient for you to work in dimension 2. Now, of course, from 3 to 2, it's not a big deal. But if the vector was not 2-dimensional, but had 100-dimensional, then it would be from 100 to 100 squared. So I just gave an example of dimension 2, so I can write it on the board. But really, the mapping is from n to n plus 2. Yeah, 1 plus 1 is 200, which means it's quadratic. Okay? So it definitely saves you a lot of time.
I have a couple more questions, but you go ahead. Yeah.
Alright, I just have a quick question. What is Z here? I don't quite understand Z. Why we're calculating the distance between Ti and Z?
So first of all, you should have asked this question before. Same for you.
Yeah.
You should ask these questions because, as I said, everyone has this question. So Z, look at Z ranges on all the examples. It was in the previous slide. Z ranges on all the examples. Z ranges in D and in P. Okay?
Previous example.
It's ranges on all previous examples
Okay.
on which we
S?
made
I
mistakes.
didn't ask this, but I thought you mentioned it, so I didn't ask
So-
it. What
so
is
S-
S and what is TH theta?
Okay. So
So many
here,
terminologies.
what is S? S is 1 if it's in P and minus 1 if it's in P. So everything is written here. Just go over it.
Yeah, and what is TH theta? TH.
It's just a threshold.
Threshold.
Yes. It's basically a shortcut of writing minus theta
It's
sign.
not a sign,
Yeah.
it's a threshold.
And what is the general goal of this kernel function? So it seems like it reduces the dimensionalities a little bit. Like the goal of the kernel-based methods.
So go over the slides again and ask this at the beginning of next time.
Oh, okay.
But please ask, because otherwise, because if you will not get it from looking at the slides, other people will also not get it, and I want to go over it again.
Okay. Thanks.
Just a little bit of clarification. So for the kernel method, the model that we learn eventually is just a set containing all the instances where we make errors. And that's just a set M and S. That's the model we learn eventually.
Say it again.
So
We learn the perceptron at the end.
okay, but like in the normal setup, we learn essentially the model is a weight factor W, right? That's what we learn. We use that to compute. Give it a new example. We use that to compute to classify it.
Right, but if we do the dual, if you use the dual representation, then we don't represent that one explicitly.
Right, but like what we
Instead,
get.
we represent it as a linear sum of x.
So for classifying like new examples, we just use that.
So you never keep W, you just keep all the previous examples.
Okay, yeah. Thanks.
Yeah.
So while I'm trying to calculate the accuracy for the perceptron average, it is working fine on synthetic data. When I'm running it on the real data, it's taking too long.
So
How
you
much
should
is
have
too
asked
much?
it. You should no. You should have asked it because I hinted on that. I told you it's going to take you.
Yeah, but how much? I will understand how much is too much.
So if it takes you 20 minutes, it's too much. If it even takes you, in fact, probably 5 minutes, it's too much. So that means that your implementation of the average perception is not efficient.
But
You can
in the
implement it
synthetic data, it's like
because the dimensionality there is 200, or yeah, something like this, 200. And what is the dimensionality of the data?
something like very high.
200,000 or something. Okay? So that's one of the lessons of this problem set, to show you that toy problems may not tell you the truth.
So what I am doing in the cumulative weight vector is I am multiplying it by the count weight.
Yeah, you're doing it right.
Yeah.
It's just that you're not doing it efficiently, and there has to be some trick in the implementation, and I'm not going to tell you now what the trick is.
I mean, it is the hint or suggestion on that.
So think about the fact that the vectors are very sparse. The 200,000 dimensional vector are very sparse. So when you think about how to implement the average perceptron, think about how to do it in the presence of sparse vectors. So also go to the recitation and discuss it, because they are going to talk about it. Same questions?
Thank you.
Sure. Yeah, I'm good, thanks.
Just a quick question. So for nonsense, is it like you define it?
No, it so happened. This is,
This is like nonsense. No X1.
so actually, what I want to say here is that for the dot product, for this to count for the dot product, I need that these both are going to be 1.
Yeah, but here there's nothing. So how can we say that this is
Okay, so this is part of the story. I'm not saying that it's always the case that it's one. I'm saying that you need, what I meant to say here is, this is kind of part of the whole story that I told, that for this to contribute to the dot product, you need this to be one. You agree with that?
Yeah, I agree.
So that's what I meant here.
Yeah, but my question is like, this is the same, right? So for the subset, there's a null, always a null subset. The same.
Yes.
So if there's like no judging criteria, how do we know that the output of this will be one? Like we don't know even it's like x1 or x2 or x3 whether they are in or not or they're gate. We don't know anything about that. How can we say that?
Okay, so strike this line. I think the way the line here appears confuses you. So basically, I'm trying to give an example of why this is right, or prove this by example. And what I'm saying is, of all the 27 monomials, those that will survive are those for which phi of x and phi of z are going to be 1. And this is the first thing. And then these surviving monomial are these, they're not x1 and x3. And then I'm explaining the subset. So the order should have been, this should have been the top line and said, I want this, I will get this from these monomials. So in terms of how to present the story. That would convince you?
I think that's not quite asking. I'm just saying that. So I totally understand those two lines. You're saying that if not x1 and x3, we use that as a conjunction, then we will get one on both cases.
And therefore they will contribute to the dot product.
Yes. So I'm asking that for the subset of 2 to the power of c, there's always a null.
Yeah, null is gonna, by default, is going to contribute. So the null is 1 always.
So we define that.
I defined the empty conjunction. Oh, okay. I didn't understand that was your conclusion. Okay. So by definition, I said that the empty conjunction evaluates to 1 on everything. Okay, good question. Okay, so that I will add this to the notes.
Because I thought there's no criteria, so probably.
Yeah. Okay, so I'll add that.
When you say null, you mean like nothing?
Yeah.
Zero conjunction.
Empty.
Yeah, empty
Depends on
conjunction.
what you think is good. Like, why is it? Why would
It's an issue of definition, right? Otherwise, I would have add 1 to the product.
Yeah.
Right?